Jai Hind everyone, I am Dr. Sanjay Sharma. Today I am here to discuss my another complex topic, and the name of my topic is uh, Stokes theorem. Today I am going to discuss basically what is Stokes theorem and how it helps us to basically convert the triple integral like volume integral in terms of surface integral. It's a very helpful theorem where we can convert the volume into its surface integral. So before to move on directly on Stokes theorem, here we must understand some very important terms. Those are related to the Stokes theorem. Before understanding these all fact and definitions, we are not supposed to understand the basic concept behind the Stokes theorem, right? So the one very starting at the very initial stage, we must understand what is a point function. So basically student, a variable quantity whose value at any point in the region, point may be anywhere in the region of space depending upon the position of the point. This position is called the point. This point is called the position of the point, right? And this position of the point can find out the point functions, right? So there are basically two types of point function. Number one is scalar point function, right? So you can first take the scalar point function, then second the vector point function. Basically Stokes theorem work on vector point function, but it can also be applicable for the scalar point function. So remember, when we are talking about a point function, then we can have the position of the function, but it depends upon the scalar function and it's depend upon the vector function. Another point, now what is scalar point function? I'm talking about a point whose coordinate are x, y, z in the region R in any space. Then there corresponds a unique scalar function fp. Then this f is called the scalar point function. So related to the region, there is a point function which is called the scalar function, right? For example, the temperature distribution in a heated body, density of the body and potential due to gravity are old examples of the scalar point function. So now we understand what is scalar point function. Now I am talking about the vector point function. Similarly student, if there is again a point px, y, z in the region R in the space, then there is corresponds a unique vector function. This time we must understand about the function p. It must be a vector quantity, then this app is called the vector point function. If I am talking about example, then the velocity of a moving fluid, gravitational force, those are the examples of the vector point function. So during the verification or the solving of any example, those are related to the Stokes theorem. When I am talking about the vector point function and then I am talking about the scalar point function, so it must be 100% clear to all of us then what I am talking about basically. So now vector differential operator, there is one operator del. Basically we have to use this operator most of the time during the calculation of vector related to the integral. So we must understand what is basically vector differential operator. It is read as del, right? So the vector differential operator del is denoted by del and also called the nabla, right? It is defined as, when I am talking about del, then basically in vector form, its value is equals to del by del x I, del by del y j, mean del by del y is the partial differentiation with respect to y, plus k component of del by del z. So this is the basically meaning of the del operator, right? Now one more operator is there which is called gradient of scalar function. When we are talking about Green, Gauss and then Stokes theorem, finally we must understand what is called the gradient in the vector function or similarly in the scalar function, right? So when, let's suppose there is a function phi x, y, z, this is the scalar function. Now understand what was the scalar function, then its gradient is denoted by, basically the grade of this phi function is called grade f. It is defined as below. So when we are looking for the grade on phi, then the meaning of the gradient is we must take the partial differentiation of the scalar function f with respect to x. Similarly, we must take the partial differentiation of phi with y and then we have to add the partial differentiation of phi with respect to z. So this quantity is called the scalar function gradient. Simply it can also be written as then grade phi is equals to del of phi. Basically this is the del on phi, correct? Right. So now geometrical meaning of gradient, listen up, like we are calculating the gradient, so we must understand what is the meaning of gradient. To calculate gradient, basically this equation, let's suppose there is an equation phi x y z equals to c. This equation representing a family of surfaces for different value of the constant c. We can have the different values of c, we can have the different family of curve surface, right? So then this gradient phi of the vector is the vector normal to the surface. Listen up, there must be a surface, student, like this is a surface, and this function, let's suppose denoted by phi of x y z equals to c, let's denoted by c. Then student, the perpendicular vector to this surface is called the vector normal to the surface, and which is the meaning of the basically gradient phi. So when we are looking to have the outward unit normal on any surface, then we are basically looking for the gradient of phi, right? Moving further, so let's take one example related to the how to calculate the outward unit normal vector. Basically this is the perpendicular direction. So I have one example here. We must find the unit normal surface of this surface at the point -1 and 2. Here -1 value is for x, -1 value again is for y, then z is for 2. Okay, so let's first of all denote this function phi, this given surface, by phi x y z equals to x y cube z square. Okay, this is given to 4. Now we must take the partial differentiation of the surface with respect to x, with respect to y, then z, and we must calculate the partial derivative. This is very simple. We can differentiate our function with x, with y, and then with z, right? No problem. Now basically this is the vector normal, but the points are given to us -1 plus 2. Then we can take x equals to -1, y again -1, and then z 2. So this is the normal vector, and obviously you can see there is a position vector and we can identify the position. So on this surface, student, on this surface the unit normal vector can be calculated by this way, right? So now we have to basically looking for the unit normal vector. So you know very well that in case of vector quantity we can find the outward unit normal by dividing the gradient by its absolute value. So we can find the absolute value. Here we get 1 upon under root of 11 with I 3j and minus of k. This is outward unit normal vector. I hope you can understand this question properly. Now I have another example for you. What we have to calculate basically in this example, we are looking for the angle between the surfaces, right? We have two surfaces. This is the mean x square plus y square z square equals to 9, and I have another surface like z equals to x square plus y square minus of 3, right? At the points are also mentioned here, and the points are 2, -1 and then 2, right? So basically student, here we are having two surfaces. So we must calculate the first, mean the normal to the surface, mean the gradient of the surface. We can have this, we can differentiate this entire function with respect to x, with y and with z. So we will have this type of expression, no problem. Similarly, we can take the values of x, y, z here, we get n1. Similarly student, we can have the n2 on the same value, right? So now I have the n2, mean second gradient value of the given surface. Now you know this is very famous formula. When we are looking for the cos theta, mean angle, then we will have n1 dot n2 equals to mod of n1 n2 with cos theta. With this relation we can have the cos theta value, and we have obviously calculated all the gradient value. By taking all the values we can have the cos theta equals to, similarly student, we will have the value in terms of theta cos inverse minus 8 upon 3 under root 21, right? So now we can understand the angle between two surfaces, we can have the gradient of the surface, right? Okay, now moving forward, this is very important, directional derivative. So here we must understand what is the meaning of the directional derivative and where it helps us during the calculation of these three important theorem like Green, Gauss and then Stokes theorem. So what is basically directional derivative? the component of gradient, right? It was gradient in the direction of any given vector is called the directional derivative of phi in the given direction vector, right? So when we are looking for the directional derivative, basically we must give in one scalar function, understand? We can find the gradient on this scalar function, nice. So now we have one vector quantity. Now we are looking for the directional derivative, then we must also give in one vector. So hence, what is directional derivative? We can have the product of the given vector and with the gradient of the vector. So this product, that definitely it must be a scalar value. So it gives us the directional derivative of the question, where student, this is the outward unit normal vector which we can find out very easily, right? So where we use basically directional derivative, yes, the directional derivative is the rate at which the function changes at a point in the direction of the given vector. So it can basically calculate the changes of the vector function at any point in the direction of the given vector. So basically we can have the direction where vector is given to us, we can find out the direction, right? It's very helpful. So we can find the rate of change of the function in specified direction, we shall calculate the directional derivative. Basically to calculate directional derivative, we can have the changes of the function in any specified direction. So it was basically the application of directional derivative. Now we can have one example based on directional derivative. Here phi function x, y, z is given to us. The function is x square yz plus 4x z square. We must calculate the directional derivative of this function, where the points are also given to us, and the points are 1, minus 2, then 1, and also there is a direction vector is given to us. Basically student, we must calculate the gradient of the phi. Yes, we can have the, let's denote this function by phi x, y, z. So first of all, to calculate basically directional derivative, we must calculate the directional the gradient value, right? So gradient is nothing, it is the partial derivative combination on the scalar function given to us. We will have the differentiation of this question very easily later. Student, we can put the values of x here 1, then y is minus 2 and z is 1. So finally after solving this expression, we will have this vector. So now we have calculated the value of grade phi, right? So to calculate the directional derivative, now we must understand and we must calculate the outward unit normal vector, which is basically equals to the vector A by dividing its absolute value. So we will have the unit outward normal vector. Now what was basically directional, you can say directional derivative. So it is basically given by what? The directional derivative is given by gradient phi with the dot product of the given vector. So here we can have the product, and you know very well student, here I, because I is 0, so I component is 0, j dot j is 1, so it must be 2 into 1, that is sorry, this is I, right? It must be 0, so minus 1 into 1, it should be minus 1, and 6 2s are 12, that is minus 12. So we will have the directional derivative of the given function minus 13 by 3. Okay, so student, now at this moment, at this stage, now we understand the basic concept we have to use behind the integral, right? So before to move on the Stokes theorem, now we must understand what is basically surface integral. As earlier I have already talking about the Stokes theorem, and Stokes theorem can convert the volume integral into its surface integral, and the reverse is also possible, right? So first of all, we have to understand what is surface integral. So let's say I am having one single type of surface here, right? So if I am looking to have the what is the surface area of this part, right? So I have just explained it here, right? So this is basically we are looking for the surface integral. Let there is a function of x, y, z whose surface integral I am looking, right? So let we have a function defined on the surface. Yes, I have talking about x, y, z. Break up. First of all, to get the surface integral, student, we must break up the surface into many small pieces. I have already break up here, right? Then multiply the area, okay, of each tiny piece by the value of the function of the point in the total piece, right? Listen up, I'm looking for the area of this small piece. Then we have to take the product of the function and then we must take the surface of this piece. So in this way, we can have the surface of any single piece, right? And we must add them. By adding up, we can have the entire surface area of any, you can say, surface. So now this is basically very simple process. If we have, let's suppose, many pieces in any surface, we can divide the surface in any number of pieces. So first of all, we must calculate the surface area of single piece. Then we have to add them and we have to add till all the pieces get covered, right? So this is basically the process behind the surface integral. We take the limit as the area of the tiny piece approaches to the 0. So this is the process. So the quantity so obtained is called the surface integral. That is the logic behind to getting the surface integral. Okay. Now moving forward, students, surface integral of vector function. Basically, in this process, we can have a function, right? So it may be a vector, this is not the vector quantity basically, this is the scalar quantity. So what happens when we are actually fighting with the surface integral of the vector function, right? So here is the process. Let f be the given function, okay, and s be the given surface where this vector is working over. Then surface integral of this vector f over the surface s is defined by basically integral of the component. Listen up, student, one more time. If we have a vector function over the surface s, no problem, then basically to calculate the surface integral of this vector f over the surface s is equal basically to get the integral of the component of f along the normal to the surface. If we get the component of the normal of the surface in the direction of f, then we can have the surface integral. In mathematics, basically the same thing can be written as, if we are looking to have the surface of this vector, then we must take the product of vector with the outward unit normal vector lying in the surface, and it may be multiplied by the ds, where n is the unit normal vector. So in case of vector, we must use this you can say phenomena here, right? Interpretation of surface integral. Basically, what is surface integral? To take a look here, if the vector field f represent the flow of a fluid, let us assume that this vector f, okay, representing the flow of a fluid, then the surface integral of f will be represent the amount. What is the meaning of getting the surface integral? Basically, it is showing the amount of fluid moving through the surface per unit of time. It is also, basically this is the definition of flux. So what is flux? Basically, flux is the, you can say, if you are talking about a fluid motion, then it is the amount of fluid which is moving through the surface per unit of time. So this is the process of getting flux. So basically the interpretation of the surface integral, we are looking for the flux, right? If water is flowing perpendicular to the surface, a lot of water will flow throughout the surface and the flux will be large, because if water is get throughout, then the flux will definitely improve. Okay, so it can tell us the amount which is just going out through overflow, right? If water is flowing parallel to the surface, yes, let's suppose this is the surface and water is obviously following parallel to the surface, then what happen? Water will not flow through the surface and the flux get zero. Definitely, if water is going in the direction of the parallel to the x-axis and the surface, then obviously flux get zero. So when the water is following through the parallel to the surface, then there is a chance to have a large amount of flux. Now, evaluation of the surface integral, student, how to calculate the surface integral? It's very easy. That the function f and the surface both are given to us. We can have the normal to the surface. We can find the normal by getting basically the gradient of f, because same process can be handled by the gradient. So now we must find out f dot n, find ds. Obviously we can find the ds, the amount right? So student, here basically we will have three type of ds, the surface area of the small amount, right? Basically if we have k component with n, then we must have dx dy over there. If we must have dy dz here, right, then there must be y and z are there, then obviously student x is missing, so we must take it mean I dot n cap. Similarly student, if we are looking for this is dx dy dz, and student we can have dz dx in case, then we must take the product of j with n cap. So basically these are the conjective formulas to find out the value, and this is basically the projection of S on xy plane. This is showing the projection of the plane on xy, this is showing the projection on yz, and student this is showing the projection of the surface on z-axis, right? You can find the where you are looking for the individual question. Evaluate resulting double integrals, and there is very simple process. So student, now basically before to finally move on the Stokes theorem, I have one example for you where basically we are looking for to calculate the surface area. This is very important question student. So I need to calculate f dot n cap ds where a vector is given to me. This is the form of the vector. S, where S, because S is the most important part of the double integral in case of vector. So the surface is given by this equation, and this is showing that this is a plane, right? And we are looking to have the double integral, or you can say surface integral, in its first octane. So the process is very easy. First of all student, when the surface is given to us, we will have the gradient of the surface. So this is very simple process. We can have the surface, we can have the gradient of the surface, right? Now we will have the outward unit normal vector on this surface. So we can find the outward unit normal vector by dividing the vector by its perfect value. This is 2/3 I, 1/3 of j, and 2/3 of k. Okay. Now we must calculate to get the integral, the value of vector a dot n cap. So here is the vector a, and here is the value of n cap. You know, I dot I become 1, so it must be a quantity in x, y or z variable, because student I dot I become 1, then j dot j become 1, then k dot k also become. Now I have a surface value. Student, basically this is the value of a dot n cap. No problem. There is a problem. Basically we are dealing with the double integral, and you can count there are three variables. We have x, we have y, we have z. So but one more thing is there, because the curve in 3 is given, you can eliminate z from this equation. So student, if I am getting the value of z, it is 6 minus 2x minus 2. So here in place of z we can have the from this relation. Now my entire curve converted in the form of x and y. Finally, I got a n cap equals to 4. So we will have basically, now we calculated the value of a dot n cap. Now by using the projection on xy plane, we must use this formula, because we need to calculate the projection on xy. Now this is k dot n cap, obviously because this is n cap, so only n cap take place, rest all I j k becomes 0, so it is 2/3. Now student, getting the integral, which is double integral a dot n cap ds, we will have the value of the k dot n cap, there you are, then dx dy, and it was the value of a dot n cap. We can very simply integrate this question. Now the only things is to calculate the limit on this question, right? Basically it is the representation of the given curve, right? So now how to calculate the limit? Basically we can have the two parallel streams, one in parallel to the x-axis, another is parallel to y-axis. So student, we can have the limit of z here, in y here in terms of x, and we will have the limit of x. It's lie from 0 to 3, it is very simple, and y basically lies between 0 to 6 minus 2x. We will have the, but definitely we can get the answer in 2 minutes. This is basically by getting solving. So this is the 81 answer, unit square. So student, we can now understand how to calculate the surface integral by getting this example. You can have different example and you can evaluate by your own practice. Now moving forward, as we have to discuss in Stokes theorem the volume integral as well. So it's very simple phenomena. In case of a volume in 3-dimensional shape, we will have a function defined over the region in a space, break up the region in many small pieces as we have converted in the case of surface, multiply the volume of each teeny space, because student it's a solid body, so it must have the you can say length, breadth, and obviously there must be a height. So we must take the volume of each piece and we have to multiply them, and we have to add all the product so that we can have the volume, right? So the quantities obtained is called the volume integral. Now student, this is Gauss divergence theorem. So surface integral of the normal component of vector, this is the statement basically of the Gauss theorem. So the surface integral of the normal component of a vector function f taken round the closed surface S is always equals to the integral of the divergence of f. So mathematically student, if we are looking for this Gauss divergence theorem, then the theorem is saying that the surface integral is always equal to the volume integral of the divergence of f. They are 100% equal. In case of triple integral, we must calculate the divergence of f, and in case of double integral, we must calculate the value of f dot n cap ds. So basically the f dot n cap ds and the divergence of f, when we are looking for f dot n cap ds in surface integral, when we have calculated the divergence f, then we are getting basically the same values. So here I have taken some graph. So you can say there is a moment of the projection. So you must understand how to calculate n cap. This is the most important fundamental here. In some case you can have 100% confirmation about the n cap. In some case you can understand how to calculate the value of the n cap. I have an example for you. We must find out the value of f dot n cap, where f is given to you, surface is given to you. What happen in case of surface? It's a sphere whose center and radius is given to you. So this is very basic simple work. You know, we can interact this question by the Gauss divergence theorem. Instead of getting f dot n cap ds, we will have the divergence of f. Divergence, you can find partial derivative of the given function with x, y, z. Okay, and by differentiating this 2x, we will have 2, this y we have minus of 1, and z we have 2. So it's a 3 of dv, mean 3 of v, right? Now student, what happen when we are actually looking about a sphere whose radius is 3, then obviously it's a tan plus 2 rated formula. We will have the volume. Volume is 4 by 3 pi r cube. So r is what? The radius is given to 3, it's 36 pi. So student, because I need to take the thrice of the volume, it is 108 pi. So it is the calculation of the you can say double integration with the help of the Gauss divergence theorem, which convert this theorem into triple integral. I have another example. We must calculate the surface integral bounded by the curves x0, y0, z0 and xyz equals to xyz both are equals to 1. Then we must calculate the triple integral. So student, again we must use the theorem. Instead of getting f dot n cap ds, we can have the volume, we can have the divergence. So here with respect to x, y, z, we will have this type of expression. Now we simply convert this integral in 3 terms, right? So what happened? First of all, we basically here, because y is not available, so we can simply differentiate, integrate the question. We will have the limit, because x lies from 0, 0 to 1, 1, 1. So student, we will have this type of expression, right? By getting all limit, the answer is 3 by 2. Now moving forward, what is Stokes theorem basically? So student, it's the theorem that is relates surface integral to line integral. Basically what is Gauss divergence theorem is doing? It can convert the double into volume, but the Stokes theorem can convert the you can say double integral into the surface integral. So student, when we are basically calculating the line integral of f dot dr, it is mathematically equals to the curl f dot n cap ds. Here this is showing obviously the value of n cap, that is very important in case of the n cap ds. So these are the direction of normal vector. Basically they are depending upon the rotation of c. So student, I have last example for you where I need to verify the Stokes theorem for the vector function given to you, and obviously it's a rectangular form of xy plane which is bounded by x equals to 0 xa, y equals to 0 and y equals to b. So basically what is going on, first of all we have to calculate the line integral of this question. So basically I am looking for the f dot dr. Dr is given to you, which is equals to basically r is what, xi plus yj plus zk, and it's a two-dimensional xy plane, so we must avoid z. Simple. We can have f dot dr, we can have the values of f dr, and we must integrate over the curve. So here we will have four type of region, OA, AB, BC, CO. You can have the answer of each phases. So basically by getting the integral, the combined answer is given to first phase a cube by 3, second phase it is equals to ab square, third phase it is 2 of ay. Okay. So by adding all the values, so what is the answer? Now by getting entire answer, yes, by adding all the phases we have the answer that 2ab square by calculating the values by you can say Stokes theorem in case of line integral. Now final, we must evaluate the right hand side of this Stokes theorem, which is curl f dot n cap ds. We can have the curl value, it's the del cross f, we have the answer y z k y for y k bar, correct. So we can have the values of the n cap, because this is xy plane, so we will have the n cap equals to k. Finally student, by taking the product of curl f, we have 4y dx and dy. Basically by taking limit, you can see your answer get verified. So student, thank you very much. It was the verification of Stokes theorem. You can have different question and you can have different type of policy with different type of question. Thank you, Jai.